really nice seminar from Professor Cecilia Leal. Today, it's my pleasure to introduce Professor Qian Chen and to welcome her to Colloquium for Material Science and Engineering. Professor Chen is a Rochef faculty scholar and associate professor in the Department of Material Science and Engineering, and she also has affiliate appointments in chemistry, chemical and biomolecular engineering, Carle, Illinois College of Medicine, and the MRL. In her research, as we'll hear about today, simply stated, she makes movie stars out of small objects, tiny objects in soft materials, by watching their dynamics in motion in real time. So her research aims to understand how nanoparticles, active materials, living cells interact, how they come together, how they assemble. And a key element of her research lies in using electron microscopy to achieve, in some cases, atomic scale resolution imaging. And in some cases, to track even individual ions and atoms in chemical reactions. So in some cases, right, this has led to strikingly beautiful videos and fundamentally new insights into a wide range of systems and polymer membranes, self-assembly. But her work goes beyond just looking at movies and making movie stars out of tiny objects, right? So in addition to her experiments, right, her group has also a really impressive record in using deep learning-based analysis to quantitatively understand these phenomena and reveal interesting underlying physics behind them. So she's been highly productive at Illinois. She's had numerous publications, impactful publications in high-impact journals, even many over just the last year alone. She received her BS degree in chemistry from Peking University, and then her PhD from University of Illinois, actually in this department in 2017, where she studied self-assembly and organization of Janus particles with Professor Steve Granick. She was then a Miller Fellow at UC Berkeley, where she became an expert in electron microscopy of soft materials, and she worked with Paul Alvasatos. So we were then really fortunate to recruit her back to the University of Illinois, where she started her independent research program as an assistant professor in 2015. She's received numerous awards, in fact, so many that I don't want to go through the whole list, so that you can get started, but a few highlights. She was the she received the Air Force Young Investigator Award, NSF Career Award, Dean's Award for Excellence in Research from Granger College of Engineering, actually twice. And she was named the Sloan Fellow in 2018. These are just among some of the many awards that she's won. She's also on the editorial advisory board for ACS Applied Nanomaterials. So in my personal experience in working with her, she's a deep thinker, and she really is excellent at pursuing curiosity-driven science. She's really brave and successful in asking kind of the why and the how questions about how things actually work and why. And she's an expert at revealing how these complex systems work with really clear and concise explanations that report the underlying physics. And so for all of these reasons, right, we're delighted to have her as our colleague, and we're extremely delighted to have her here today to listen to her research. And so please join me in welcoming Professor Chen to the seminar.
Thanks, Charles, for this heartwarming introduction. Hi, everyone, this is Qian. Today is my greatest pleasure to share with you my group's recent efforts on charting the order and heterogeneity of nanomaterials. So let me go back to where all it gets begin. So at the very beginning, 8 years ago, when I started my faculty career, I had a few empty rooms. I had 2 PhD students, Bingbi and Zihao, shown in the photo. I had something more. For example, a rejection note for my first NSF proposal on the idea of using electron microscopy to image soft materials. So the concern was about electron beam effects, and that was a concern that has intimidated many. I was sad about the rejection, not realizing 3 months later, I would receive an even more cruel rejection on our first paper. So it appears that publication in any form will be premature at this time. So if you're familiar with the ACS reviews portal, you will recognize this is basically the worst level. There's something positive, of course. I went to MIS as a faculty for the first time to give an invited talk. I got a lot of greetings. One of the greeting is, "Who are you? I have never heard of you in the field before." That's because I instead studied a new direction in my own independent research. We actually didn't synthesize any nanoparticles until I studied my group. And you will hear a lot about nanoparticles in my talk today. And sometimes there could be rejection from the weather. So this is a photo of my lab after a heavily raining day. You can see the ceiling was leaking, and also we have sensitive electronics on the floor. But fortunately, that has never happened after Paul Brown became the MRL director. So this is how my group look like now. You can see every one of them is happily in front of their favorite instrument. The idea of utilizing electron microscopy to image soft materials has been recognized, has become the foundation of a lot of funding opportunities shown here. I'd like to mention, including this soon to start STC Center, where I'm a co-PI. And as to the very cruel rejection I mentioned earlier, I learned a hard lesson. And the hard lesson was not about how bad our science was. Our science is never bad. It was about the importance of telling the right story to the right audience. And that's a lesson I still keep in my mind even now. So we completely rewrote our introduction and resubmitted the paper 3 months after the rejection. And now this paper has become the foundational paper of ours to solve the electron beam issue and has become the most cited papers in our proposal writing. As to MIS, I'll become the meeting chair for the 2025 spring MS meeting, so I guess more people will be forced to know more about us. So with all those years, you can see we have ups and downs. A lot has happened over the last 8 years. We have tried a lot of different systems with a lot of different experiments. In the end, we find ourselves consistently coming back to 2 key concepts, that is order and heterogeneity in materials. So let me illustrate to you those 2 concepts using this beautiful paper in astronomy. So this is about the structure in our galaxy system. This using very advanced imaging and spectroscopy methods, people are able to capture the presence of metallicity with large spatial variations. So I'd like to highlight 2 keywords here. The first is metallicity, which is usually associated with order. And order is a very important aspect of matter. For example, if you look into the history of Nobel Prizes, a lot of them were given to state-of-art characterization and concepts to measure order, such as XRD crystallography and quasi crystal. At the same time, the main breakthrough of this paper is actually about the measurement of spatial variations in the universe. So there's all those headlines about, oh, the Milky Way is actually not uniform, which is a surprise. Or the Milky Way turns out much messier than what people thought. So this concept of heterogeneity is a more recent concept. That's why the associated Nobel Prizes are also more recent. I'm giving 2 examples here. The first is with the James. His awarded contribution is based on his application of theories of simple crystals to complex material systems. And the most recent one is to climate kills, which has nothing to do with material science, but somehow it shows sometimes you really need to have a completely different mindset if you are dealing with complex systems that can be dynamic, that can be hard to predict, that can be spatial temporally heterogeneous. So these 2 sets of materials, order and heterogeneity, is going to be the main focus of my talk today. These 2 concepts has been there for a really long time, and we do have new tools to give us new insights. So in particular, in our group, we focus on this collection tools of electron videography. So electron videography focuses on electron microscopy. I'm sure some of you in the audience have the experience of using electron microscopy to really insert a dried or frozen sample into the high vacuum electron microscope to image the size, shape, and spatial distribution of a sample at the nanometer resolution. So what we are able to do is to go beyond just capturing a 2-dimensional projection view of your sample in a steady state. Instead, we can actually take movies. And we have 3 different ways to take movies. The first is liquid phase TEM, showing here, which allows you to use 2 membranes to seal and sandwich a liquid sample and then put it into the high vacuum TEM. So by doing so, not only you can resolve the nanoscale structure, you can also visualize the vivid thermally agitating motions in the presence of solvent molecules. We can also have electron tomography showing here, which means you can connect all the different 2-dimensional projections of the same sample at different orientations into one movie. And from this movie, you can reconstruct the 3-dimensional nanoscale morphology. Well, we can also have 4-dimensional scanning transmission electron microscopy or 4D scan. This is a technique that allows you to focus the electron beam into a nanometer size probe. And then this electron beam can interact with a nanometer by nanometer size of your sample, generating one electron diffraction pattern. And then as shown beautifully this animation made by James Watt's group, you can then rest scan this electron beam probe to collect a two-dimensional array of electron diffraction pattern. From those patterns, you can map out the phase orientation, and strain at the otherwise inaccessible nanometer resolution. So with those tools, my group has been focusing on this common thing of understanding the formation, the control, and the function of order and heterogeneity at the nanoscale. We have experimented with a lot of different systems. We can take movies of colloidal nanoparticle suspension to look into their phase transition. We can take movies of biomolecular dynamics. We can take movies of polymer morphing. We can also take movies of electrochemically driven phase transformation. Indeed, we find one common scientific message in all those systems is that the order and heterogeneity at the finest atomic and nanoscale can impact their bulk property. So now, let me start from the first vignette on the realization and formation of order in colloidal nanoparticle suspension. So colloidal nanoparticle suspension is the first software material system we dive into. So this is a photo of my former PhD student, Ariane, who basically collected all the possible awards in her PhD and postdoc study. So she's holding in her hands the solutions of colloidal nanoparticles. And those solutions have reddish, orange, or bluish color because the nanoparticles inside have different shape and size. And then those colloidal nanoparticle solutions are very intriguing materials because they can easily be synthesized in large scale in solution. They have solution processability, and they can also have composition, size, and shape dependent properties. For example, the red lines you see in the rapid COVID test, those are the color of gold nanosphere solution. And now you can see more and more quantum dot-based TV displays out there. And then in the context of colloidal nanoparticle solution, ordering is a very intriguing question, as beautifully demonstrated in this chemical review paper here. This is because the periodic superlattice self-assembled from colloidal nanoparticles can have architecture-dependent optical, electronic, catalytic properties. And broadly speaking, in nature, a lot of biominerals are essentially composed of nanoparticle building blocks. However, for a long time, when you think about those nanoparticle superlattices, you only have single snapshots, and that's because electron microscopy with the needed nanometer resolution to see individual nanoparticles cannot be compatible traditionally with a liquid sample. So you can only insert a dried or frozen sample. It works at high vacuum. As a result, you don't really have dynamics. You do not really know how out of a colloidal suspension that was held in Ariane's hands, those individual nanoparticles undergoing random Brownian motion can come together to form into an order structure. Modeling of this process has also been very difficult because the colloidal interaction at the nanoscale is non-additive. So here comes my group's unique contribution to the field. We introduced liquid phase TEM to capture the complete crystallization process of a colloidal nanoparticle suspension. We have two ways to do liquid phase TEM. One is to use this microfabricated chamber to make sure we can sandwich and seal a liquid sample. At the same time, we can also do in situ stimulation. We can change the solvent, change the temperature, and also apply electrical bias. We can also do a graphene liquid cell showing here, which has wonderful contrast and minimize electron beam effect. So as I talk about electron beam effect, this is all because electron beam has high energy. And if you are taking a continuous movie, that also means you are showering your electron beam continuously on your sample. And sometimes that can fundamentally change the nature of the sample, such as showing here. You can use electron beam to induce the corrosion of gold nanoparticles in a graphene liquid cell. So that's why the first few papers in my group is really trying to do a few beautiful control experiments to identify the good electron beam intensity or electron dose-rich regime, within which we do not need to worry about electron beam effects. So with all that established, the most important breakthrough in my pre-tenure work is the observation of nucleation pathway of a nanoparticle through lattice. So showing here in this schematic, we're able to load an aqueous suspension of nanoparticles into the liquid phase Qian chamber, and those nanoparticles are coated with charged thiols. And then we can induce the crystallization by increasing the salt concentration in the system to screen the electrostatic repulsion. And that's actually how we can get the liquid phase TM movie showing here. In a TM movie, the black things are our nanoparticles. They're moving very vividly because they're in solution. They have Brownian motion. They're interacting with each other to form into ordered lattice. We can also do single particle tracking to allow us to chart a crystallization coordinate from which we can identify a non-classical nucleation pathway. So non-classical nucleation pathway means instead of following the classical nucleation pathway to directly form into a crystal from individual building blocks, you need to go through a collection of pre-nucleation motifs. So this is a modern mechanism that has been demonstrated in atomic, ionic, protein, molecular building blocks, and we show it for the first time for nanoparticle building blocks. I also want to mention, in order to capture such movies in a quantitatively robust manner, we need to optimize every single step of our experiment, which we included in our 75-page supporting information in this paper. So this concerns nucleation, which is the first step of crystallization. And then the second step of crystallization is the so-called post-nucleation growth habits, which is also a concept we learned from atomic crystallization. As showing here in this example, even if you start from the same nucleus, given different growth environment, you can have crystals of very different size, shape, and surface morphology. This is a concept that has been also physiologically demonstrated in superlattices self-assembled from nanoparticles. So we wonder what is the fundamentals behind. And it turns out this post-nucleation growth habits is an even harder to study question than nucleation because you are dealing with a much larger system post-nucleation. So as a result, it's both experimentally and computationally more expensive. And in addition, for growth habits, not only the interparticle interaction matters, but also the mass transfer properties such as diffusion, also flux start to matter. So that's why it becomes a complicated multi-scale dynamics question. So we took the experimental challenge anyways. My former PhD student, Bingbing, was able to substantially upgrade our liquid phase TM imaging protocol so that now we can observe the growth of large three-dimensional crystal. Bingbing also developed and synthesized a series of differently shaped particles, the concave cubes, the flat cubes, and nanospheres for comparison. So let's look at the movie one by one. In the first movie, you can already see the crystal has grown pretty big, so it's definitely post-nucleation. If you look at the growth front, you can see the incoming particle will only complete one layer before you grow another layer. There's actually no random fluctuations. This is a so-called layer-by-layer growth. And then if you look at the other two examples, although the shapes of the particle, the interaction potential, and also the lattice symmetry are different, they also follow the same layer-by-layer growth. Layer-by-layer growth is also a system, a mechanism that at atomic building blocks frequently adopt. That's actually why you can easily have atomically flat thin films for semiconductor industry. So does it mean layer-by-layer growth is a universal growth habit for crystals? That's not really the case. So if now we're dealing with much larger size building blocks, the micron-sized colloidal particles, so you can see the crystal become much rougher, shown in this optical microscopy movie with a scale value of 10 micron. So this first hint on the dependence of building block size motivates us to realize the diffusivity of colloidal nanoparticles, whether it's about the interlayer diffusion or in-plane diffusion, are actually orders of magnitude larger than micron-sized particles. So as a result, it's actually very easy for them to sample all the available crystal size. But does it mean nanoparticles will always follow layer-by-layer growth? That's not the case either. So it turns out this is the beauty of direct experimental imaging. It can actually help you to go beyond this theoretical expectation. In retrospect, it's actually pretty straightforward. You have a three-dimensional crystal, which means at least you have two growth directions, the in-plane growth and out-of-plane growth. For each growth direction, you will have two choices. You can be flat or rough. So as a result, you should have 4 growth modes. And your experiments were able to observe all the 4 growth modes. I'm going to highlight the 2 hybrid growth modes. So in those 2 movies, you're going to watch the particles of the same color, they are in the same layer. So you can see in the first movie, the 3rd layer already started to grow when the 1st and 2nd layer are still growing. So that means out of plane, this is corrugated growth. But if you look at the boundary of each layer, it's actually pretty smooth. So in plane is row by row growth, which indicates it's a smooth boundary. And then in comparison for the movie below, the 2nd layer will only start to grow when the 1st layer stops growing. So that means out of plane is layer by layer growth. But if you look at each plane, the boundary is actually really rough. So in plane is corrugated growth. So this is also the first time we were able to capture those 2 hybrid growth modes in solution in real space and real time. With all those experimental observations and literature, we started to have this ambition to try to establish a unified framework considering the effects of different size building blocks. So that's when we went to collaborate with Professor Eric Lawton of Northwestern and his former PhD student Zi Wei. So together they run a lot of kinetic multi-color simulations, and there are 2 highlights out there. The first is they're able to reproduce all the 4 growth modes that we experimentally observed. And second, they're able to actually sample a large parameter space to generate one phase diagram. So in this phase diagram, the x-axis is energy barrier, which is controlled by interparticle interaction. The y-axis is diffusivity over flux, which is determined by mass transport. So interestingly, the different size of particles, they can actually rise at different locations of the phase diagram. For example, atoms sit at the top, corresponding to layer by layer growth in both 2 growth directions. That's why atoms tend to form into faceted crystals. And then for micron-sized colloids, they sit at the bottom. They correspond to corrugated growth in both 2 directions. So that's why you can see a lot of rough colloidal crystal in the literature. And the beauty is in nanoparticles, they can recover all the 4 growth modes. So that's why if you're using nanoparticles as a building block, you can have a huge library and huge tunability in terms of the crystal morphology, size, and shape, as well as the bulk defect density. So with all those fundamental studies, this actually allows us to appreciate what are the similarities, also differences for building blocks of different sizes. And this can motivate us to start to I hope you are not really too surprised. This relatively wise person is me, myself. And this is actually a sentence, it's a statement I included in my research statement. So this is what I use to usually motivate myself and my group to think outside the box. As to the silver question, we have a lot of answers, but for today, I'm going to highlight two answers that are living outside the box. One is photons, and the other is topologically engineered phonons. So the story of photons really started with my former postdoc, Shan, who is now a faculty. He introduced to us the capability to synthesize highly monodispersed tetrahedral gold nanoparticles. And then my student Jiahui was able to disperse them in aqueous solution, load it into liquid phase TEM, and watch their self-assembly. So this is what she observed. So you can see, first of all, you see a beautiful lattice. But second, which is more important, you can also see a lot of voids in the lattice. So fundamentally, you will have voids because tetrahedron is a very special shape. It cannot continuously tessellate the three-dimensional space. And then what Shan and Jiahui were able to do innovatively is that first, they're able to reproduce the same porous lattice outside TEM on a silicon wafer, which is very important for property measurement and scale-up manufacturing. Second, they're able to induce this nanoscale compression to introduce this void collapsing process. As you can see beautifully demonstrated in this video, in the end, you will have a collapsed lattice with all the triangles uniformly twisted along one direction. This means symmetry breaking, and this means chirality on the substrate. So together with our collaborators, Professor Li Kotov and Jun Lu in University of Michigan and Dr. Haihua Liu in Ardon National Lab, were able to pinpoint the optical property of our self-assembled lattice. Actually, this is also for the first time for self-assembled nanoparticle superlattice. So this study really paves way for a lot of future studies. For example, this was also the first time we used ultra-fast electron microscopy to map out the optical property of a nanostructure. We can also utilize the concept of symmetry breaking in collapsing a porous material in other systems. And now we're on our way to demonstrate more practical applications with this beautiful structure. And the second application of topologically engineered phonons really started more than 10 years ago when I met Xiaoming in a postdoc session in APS. So Xiaoming was a postdoc, I was a graduate student. She didn't know much about colloidal particles. I didn't know anything about mechanics, but we liked each other, so we stayed in touch. And it's interesting, about 3 years ago, after we both become faculty for quite some time, we realized there's actually one common ground, which is our control in geometry. So in Xiaoming's field of mechanical metal materials, control geometry really controls the mechanical response of a material. So showing here, she frequently sees a structure of springs connecting beads. And then by doing so, even if you're just pressing against one bead, this can introduce phono vibrations and induce the subsequent mechanical response. So this is a concept that has been extensively realized at the macroscopic scale by top-down lithography or by 3D printing. Showing here is an example where you can encode the geometry such that the structure is very soft when you touch the soft spot, but on the other hand, really rigid if you touch elsewhere. With this mechanical metal materials, it has a non-lethal application showing here, but at the same time, keep in mind, in the nanoparticle self-assembly community, we are very good at control geometry. So this is when she and I put our minds together, start to think about self-assembled mechanical metal materials. This could be exciting. It has been barely charted. It can open a lot of opportunities because we'll be achieving phono manipulation at a length, frequency, force, and also energy scale that was not accessible before. This could introduce new concepts. For example, reconfiguration and phase transformation can now be seen as a result of phonons. And also individual nanoparticles can have their own plasmonic, optical, electronic property. So there could be a lot of opportunities to couple those properties with the generic phonon property of the lattice. And moreover, this can introduce new platforms. For example, how to measure the phonon response at the nanoscale. So since this is about geometry, I'm going to talk with you about two types of geometries. The first is Maxwell lattice, which is a concept that is known from condensed matter physics. So in a Maxwell lattice, you will have coordination number of a system equals to 2 times the dimension. By doing so, the lattice can actually freely deform without paying any energy penalty. And one example of a rhombic lattice, Maxwell lattice, is a rhombic lattice shown here. In a rhombic lattice, the average coordination number is 4. You have dimension 2, so 2 times 2 dimension is 4, which satisfies the Maxwell rule. So my student Chris was able to achieve this rhombic lattice from the sub-assembly of gold nanocubes shown in this liquid phase TM movie here. You can see the lattice actually undergo a lot of collective lattice rearrangement. I should mention this is actually the first nanoscale Maxwell lattice in action, and the large scale realization you're seeing is essentially a linear combination of soft phonon modes, which are characteristic to Maxwell lattices. So the soft modes, together with the nanoscale springs, which determines the soft modes, can actually both be measured using liquid phase TEM. So here I'm showing a series of liquid phase TEM movies of 3 different Maxwell lattices, different conditions. So here we can do single particle tracking following the position of each single particle. We can do global diffusion correction so that in the end, what we can look at is really just the local vibrations of particles at the lattice sites. And then we can derive the really amazing phonon dispersion spectrum as shown here. So the phonon dispersion spectrum has an x-axis, which is the position in the first Fourier zone, and the y-axis is frequency or energy scale. And there are 2 aspects I'd like to highlight. The first is you will always have this low energy branch in the phonon spectrum for both of the 2 Maxwell lattices. And that is corresponding to the soft modes, corresponding to the large scale lattice rearrangement. And second, as I mentioned, fundamentally, the soft modes are determined by springs. So Xiaomi was able to develop a theory to both model the nearest neighboring spring, which is Qian, and the K angular, which considers the next nearest neighboring effect. So together, using this model, she was able to fit our experimental data really nicely, so we can measure the nanoscale spring constants in the system. So if you pay attention to the values, it turns out the K angular are actually orders of magnitude smaller than the Qian, which really means the system is rotationally really flexible and longitudinally really robust, which is exactly the feature for Maxwell lattice. So this study can show you how to think about how to measure phonon dynamics at nanoscale. And the next example is a little bit exotic. So this is the exotic geometry of a moire lattice. A moire lattice is basically 2 hexagonal lattices overlaid with each other. It's a beautiful strategy to introduce structural complexity because just by changing the moire angles, you can have different units of size. You can have chiral symmetry breaking. You can also even have quasi-crystal. And when it comes to phonons, now the phonons are not only determined by the local coordination environment, it's also going to be coupled with the other layer. And this concept has already been beautifully demonstrated in graphene moires, where the moire angle can sensitively fine-tune the electronic property. So we wonder if we can fine-tune the phonon property in a nanoparticle moire. But of course, the first question is how to make a nanoparticle array. We learned from the graphene moire design and realized this really requires a separation between interlayer interaction and intralayer interaction. So that's what we realized if we use gold nano rods showing here, which is the most anisotropic gold nano building block, gold nanoparticle building block. So with the gold nano rod, you can have very strong side-by-side attraction, which can be used as the intralayer attraction to make sure you have a very coherent layer, which is analogous to the covalent bond in graphene moire. But at the same time, you can have very weak tip-to-tip attraction as the interlayer attraction, so the layers can misalign with each other, which is analogous to the pi-pi or van der Waals attraction of graphene moire. So my student Chang adopted the idea, dispersed gold nano rods, put it into liquid phase TEM. But this time he used a magic so that the gold nanorods actually stand against the substrate. So we are looking at the projection view. That's why each nanorod now actually look like a dark circle. So still in this movie, indeed they form into a hexagonal lattice. And then my student John greatly expanded the level of gold nanorods. So that's actually one unique feature using a nanoparticle building block in comparison to atomic building block. In graphene arrays, the interatomic potential between carbon atoms are basically fixed. But when it comes to nanoparticles, you can actually change the length, change the width, or change the aspect ratio of those nanorods. You can have a huge tunability space in terms of interparticle, intraparticle interactions. And then Chang further have the magic to actually have two layers of hexagonal lattice standing upon each other. And here you are seeing really a diversity of moire patterns self-assembled from gold nanoparticles. So I'm showing on this one single slide, 3 years effort. I'm showing 3 movies out of more than 200 movies. And that is because it turns out this is a really robust system to generate moire patterns. It's also because we have a huge library of gold nanoparticle building blocks out there. So we have a large tunability in terms of moire angle and the intralayer coupling. I mentioned about performance response. It's important to know the single particle position. But if you look at those movies, now even with your eyes and your brain, it becomes impossible to identify the individual particle location because you have 2 layers projecting onto the same plane. So that is when my student Le Han came up with this really smart idea. He generated a simulated library of liquid phase TEM images of moire patterns shown here, and feed that into the training data set for a neural network because they have very well-established ground truths. And then after training, now the neural network can use an input as a raw data liquid phase TEM image of moire pattern to output the individual particle locations. And then with this single particle location tracking, now we can actually map out what is the displacement vector field. We can actually map out what is the intralayer realization field together with a principal shear strain. So those features all arise because now for each layer is no longer perfectly hexagonal lattice. Instead, they will be distorted in the presence of the other layer. We're currently on the look for moire phonons. We already have some advances out there. We're also looking for topological phases and transitions. But what I really want to pinpoint here is there are basically unlimited opportunities where you marry the topological mechanics with colloidal self-assembly. There's an ever-expanding library for self-assembled structures that could be interesting, which can motivate new self-assembly strategies together with new building blocks. We also need to do practical demonstrations of phonon engineering, so this will call for more scale-up manufacturing methods. We also need new theories to predict properties. For example, previously, Xiaoming needs to consider 2 springs, consider the next nearest neighbors in order to really explain the mechanical property we observed. So that's the story about order. You can see new measurements, new movies, and also new properties, new applications. But there's another side of the world, which is complexity and heterogeneity. So I'm using this image of paper crumples. Some of you might actually seen it when you are really frustrated with paper writing. So those crumples are each different in their own size and shape. They are complex because you cannot just use one single shape descriptor to describe their size. So that's why we're looking into those materials, and I should mention such complex morphology is really everywhere. In nature, in the bacterial morphology, in the brain-gut axis, in the developing embryos. And then in the context of material science, really the ongoing technological questions are twofold. The first is, how do we resolve the 3-dimensional morphology at a nanometer resolution? And second, if we can map out those morphology, how do we quantify them? How do we quantify the complexity together with the heterogeneity? And ultimately, how do we understand the synthesis, morphology, and property relationship for predictive design? So for this vignette, this is when the other 2 electron videography methods, 4D STEM and electron tomography, will make a huge difference. Let me first start from the system of polyamide filtration membranes. So this is an active layer in thin film composites for water purification and small molecule separation. And this work was initiated by my student Johnny, together with my former postdoc Hyo-sung, who is now a faculty, in close collaboration with our David Jie in mechanical engineering and Xiao in chemical engineering. So showing this schematic here, a polyamide filtration membrane is synthesized out of interfacial polymerization, which really means you can have two monomers, each dissolved in one liquid. And those liquid phases are not miscible with each other. So as a result, you will only have polymers reacted at the interface. And then as a result, if you look at the polymer film macroscopically showing here, it just looks like one shining flat film. But if you zoom in under the TEM, you start seeing a lot of nanoscale features. And those are the features we'll later refer to as crumples. So here comes the new questions for old system. So what is the three-dimensional nanoscale morphology? And what is the morphology relationship together with synthesis and property? So as I mentioned, electron tomography is very important, but keep in mind, polymers are actually a lot more being sensitive than the inorganic nanoparticles we studied earlier. As a demonstration in this movie really shows sometimes you can literally drill a hole using electron beam onto the polyamide filtration membrane sample. So this is when our previous expertise on carefully controlling the electron dose will make a difference. With some optimization procedures, now we can actually take more than 100 images on the same polymer sample with different angles without structure damage. So this is a raw TEM2 series. If you look at this 2 series really carefully, your brain is actually a wonderful computer. You can already reconstruct to realize here each crumple, each feature is indeed protruded in a z-directional space. And then below in this computerized reconstruction, you can clearly see the nanoscale feature. And more importantly, if you follow the slices, you can actually recognize they have nanoscale voids embedded in this membrane too. And that's what we can resolve. We can apply this method to a collection of membranes synthesized at different conditions. And this is what we get, consistently at a voxel size that is smaller than nanometer. And then based on those electron tomographs, we actually have 2 discoveries. The first is if you look at those samples, although they are synthesized out of the same chemical reaction with identical 2 monomers, by just changing the monomer concentration and the concentration ratio, they can have very different morphology. We later realized by measuring the intercrumple distance that this morphology development is actually controlled by a Turing theory pattern. So what this means, this is usually used to explain biological pattern formation. We here shows this can also explain the artificial morphogenesis of polymeric material. And next, we're also able to measure local thickness very accurately in the presence of voids. That's how we can use those morphology parameters input to accurately predict the molecular separation performance of the membrane. We have crumples in the membrane, and the crumples have arbitrary 3-dimensional shape. So in our effort to translate those arbitrary 3-dimensional shape into quantifiable numbers, here we have more than 50 descriptors to detail the shape, such as 3-dimensional volume, the surface area, the height, the surface curvature. With all the shape parameters, we start to ask us this Anna Karenina principle, where every single nanoparticle studied previously are self-similar with each other, is every crumple different in their own way. So computer tells us the crumples are not each different in their own way. In fact, if you fit the geometric descriptors of more than 100 crumples into PCA analysis and then use machine learning, they can be automatically grouped into 3 categories. We can have domes, we have dimples, we have lace. And those 3 categories, if you look carefully, they indeed have self-similar shapes. And that's something you will never guess if you just look at the raw electron tomographs, because the crumples are so overwhelmingly heterogeneous. And then later we'll realize the types of crumples are closely related with a mechanical property we measure using AFM. We also show the portion of the crumple types can be fine-tuned by synthesis conditions. So this ultimately closes the loop of synthesis, morphology, and property relationship. We really see this emergent relationship where the morphology serves as the middleman, linking synthesis and property as very important, especially for polymeric materials and nanoscale, because that's the nanoscale where chemical heterogeneity during synthesis and processing can actually happen. The morphology can be even more complicated, as shown here. So in this electron tomograph out here, we are actually looking at is now the system become a lot more complicated. So you will, instead of having spatially distributed individual crumples, now the crumples, they get merged with each other. They start to interpenetrating with each other. And now we can no longer use intercrumple distance or most of the other shape descriptors I mentioned earlier to describe them. So even just a simple question of how to quantify this morphology becomes a question. So this is when my student Fallon came up with this very smart idea of using graph theory. So in particular, she was able to apply scanitization onto this electron tomograph to simplify it into a network as shown here. This is a network composed of vertices and edges. And this is a network that is essentially the structural graph of our complex morphology. This is a really important conceptual leap because then we can connect with a huge mathematical toolbox in graph theory to quantify this network. For example, we can use a so-called graph efficiency, which describes how efficiently a graph can transfer a given node. And indeed, with differently synthesized or interconnected polyamide membranes, we can see there's a trend. And this trend in graph efficiency actually matches really well with the effective modulus of the three samples. So we see this as a starting point where you can truly have an arbitrary morphology to begin with and exhaustively quantify them. We also see this marriage with network science as a very important foundation for the XTC center I mentioned earlier. So in those systems, basically heterogeneity fundamentally originated from the generic softness of polymeric materials. So in the last system, I'm going to visit the ultimate heterogeneous system, which is a battery. So battery is the ultimate heterogeneous system because it's heterogeneous across all the nanoscales. It's heterogeneous at the atomic level because you can have dislocation, point defects, and strain generated from electrochemical cycling. You can also have heterogeneity on the ensemble, the macroscopic level, because local mechanical cracks can impact the bulk performance. So most studies actually focus on those heterogeneities on the longer nanoscale using advanced synchrotron X-ray methods and optical microscopy imaging. We focus on the much less explored nanoscale. So this is a project initiative by my postdoc Wenxiang in close collaboration with Jim and with Halpo, Paul, and Alif. So in this particular system, we use the single crystalline spinel lambda manganese oxide particles as the cathode material for magnesium ion battery. So this particle is single crystalline to begin with, which can be told from its very nice facety shape and only with one single set of electron diffraction pattern. And then when we run the electrochemical cycling, which basically means now we're forcing magnesium ions to diffuse in and out of the cathode particle. From XRD, we can see they do have phase transformation. They also have structure distortion. But from XRD, which is an ensemble measurement, you don't know the details of the structure distortion. So that's why Wenxiang went ahead to develop a series of imaging and analysis protocols to, for the first time, apply 4D step for complicated battery materials. So here, this is one reconstructed image of a cathode particle after discharge, which means magnesium ions are now intercalated into the particle. And in each pixel of this reconstructed image, corresponding to one electron diffraction pattern shown here. And from each electron diffraction pattern, you can measure the lattice spacing, you can measure the phase orientation, and so on. So eventually, we can translate this one map into a map of macrostructure. So you can map out what is the face orientation, what is the strain along different directions, and what is the strain gradient. So with those maps, this unprecedented nanometer spatial resolution, for the first time, we're able to identify the microstructure, the spatial distribution of phase domains can actually impact the ion diffusivity by more than tenfold. So this is suggesting, in addition to composition, just by changing the microstructure can be also very important for energy storage materials. So in this example, we're using a single crystalline material to begin with, and the microstructure really got formed after electrochemical cycling. And then what about we actually start to pre-engineer the microstructure even before we use the system as capsule particles. So this is the idea adopted by my PhD student Zhi. So he actually dived into some really old literature about 30 years ago, which shows the non-magnetic oxide particles can undergo a series of phase transformation when you heat it up, showing this XID result of his. And then what he was able to show is with the differently pretreated nanoparticles, they actually indeed have different performance in the application in zinc-ion battery. So for full performance here is the particles preheated at 200 degrees C. And if we use 4D stem to look at the particles, this is a particle with a lot of defects as shown here. You can see the electron deflection patterns now become very stretched. We still have ongoing studies on this project, but the immediate scientific message is that electrodes with stacking faults actually works better than single crystalline electrodes. So this is an amazing example where heterogeneity actually can win over order in material performance. So with that, I hope I show you how order and heterogeneity at the finest atomic to nanoscale can actually impact bulk performance. I really want to mention to us, this is really the future for a lot of future studies, and that's actually why we wrote 2 chemical reviews papers, both out this year, on how to rethink about heterogeneity of order, how to use the state-of-art electron microscopy methods. We also wrote viewpoint papers on heterogeneity importance on both nanomatter and matter. I also want to mention there's a big mature domain of research in our group involves biomolecular imaging and also polymer imaging that I'm not really talking at all. So this actually involves a huge group of local collaborators showing here. This got started with imaging single protein fluctuation dynamics in liquid, in graphene liquid cell, in real space, in real time. And now we're expanding it into the cell level to the tissue level. I also should mention there's another big aspect of our research on method development. For example, I talk about each individual electron videography method, but how about we conjugate them together? So connect liquid phase TEM with electron tomography, so we can see 3-dimensional dynamics. We have some preliminary demonstration showing here. When it comes to machine learning, how about we go beyond automated data analysis by making it more active to actually help and get our data acquisition? So those are the future we see. So with that, I'd like to thank the people who make it possible. A lot of my friends actually came to ask me how to balance, also maintain depth. We are dealing with so many different topics. I always answer, I learned a lot from my group. So this is a photo of them. And to show you quantitatively how great they are, this is a list of awards they have obtained on the department level, college level, university level, and also national level. So thank you all. Thank you for your attention. Happy to take any questions you have.
I guess I'll answer a question. Yeah. Questions for Professor Chen? Yes.
You mentioned satellite phase transitions in the Glutenrod and Foray. What kind?
Oh, right. That's a great question. So what happened is when you have a Marie pattern, due to the interlayer coupling, ideally your phonon band structure become very complicated. You can actually even have band gaps between the different modes. So those are the features we're looking at. If you have those features, you can have topologically driven phase transformation. That will be very interesting. So that has already been demonstrated in electronic properties of graphene arrays, but we're looking for those in this phono manipulation context.
Your Maxwell lattice kind of showed this, it looked like a truncated gold cube that is just has the right interactions, I guess. Can you say a little bit more about what's special about that particle?
Right, that's a great question. So you can imagine if you have a perfect cube, then likely the perfect cube will form into a square lattice. And the square lattice will be relatively rigid in some sense. But the fact that we have a truncation is exactly the reason why they form into this rhombic lattice. Once you have a rhombic lattice, you basically have two degenerate states in terms of structure. That's how they can actually freely rotate, switching the orientation of the rhombuses. That's actually the fundamental reason they can have large-scale lattice rearrangements.
So in the membrane, so you have this incredible complexity of the crumbles, but you put all the data through a machine learning algorithm, and it did something you might call dimensional reduction or something.
Yes.
It mapped all those things into three categories. So my question is, what do you do with that information? Is it possible that you can assign some metric, for example, permeation, presumably what's of interest?
Right.
Which could, for the minimalist model, would be you'd assign some metric for each of those three categories that maybe different membranes have different fractions of the different categories of the crumbles. Can that be used to create some type of effective medium understanding of actually what these things are being used for, which is
Right.
permeation?
Yeah, that's a great question. So there are two aspects we currently are relating those two. The first is with different morphological crumples, they actually have different local mechanical property, meaning if we use AFM to measure the pairing modulus, the modulus is actually different for each category. That's actually already important because for membrane applications, the mechanical robustness is actually very relevant. And the other thing, as you mentioned, in terms of modular separation, what we find is there are two parameters that are very important. One is what is the local membrane thickness. Okay, that is important because that's basically the solid permeation path. And the other is the void surface area, which is the void enclosed by the membrane. So for both of those two properties, they're actually different for different crumple categories. So that's actually really nice for us to be considered in the model.
Okay, so it says anyone attempted to quantify that to then.
We did that in this paper that was just submitted.
Okay.
I have a relatively naive question. So for lipid-based TM, if you're imaging materials that doesn't have a very high contrast, how do you differentiate signal and noise?
Right, right, that's a great question. So for example, I didn't mention about the polymers, also protein imaging that we have done. So first of all, if you really have careful with experiments, you can still have contrast even with protein samples. And the magic here is actually to use the graphene liquid salvage. So the graphene liquid salvage can maximize the contrast, also minimize the background from the liquid environment. So there are a certain range of samples we can image. And of course, if somehow your sample is really just having no contrast at all, we cannot really push too far with that. That's what I would think. That's actually when the element mapping capability of electron microscopy may actually help.
Any other questions? Okay. So this is a beautiful seminar. Let's thank Professor Chen again. Very, very